After studying this module, you shall be able to understand the basics of small ring compounds, Bayer's angle strain theory, synthesis of small ring compounds, and the reactions of small ring compounds. Alicyclic compounds, derived from aliphatic cyclic compounds, are the organic compounds that resemble both aliphatic and the cyclic compounds in their properties. The saturated alicyclic compounds have a general formula of CnH2n, which is same as that of an alkene and are isomers of alkenes. They do not have double bond but possess a ring structure. When the molecular formula of the saturated hydrocarbon corresponds to the general formula CnH2n, then the compound have one ring. If the general formula is CnH2n minus 2, then the compound have two rings. If it is CnH2n minus 4, then the compound has three rings, and so on. Classification of monocyclic compounds. Monocyclic compounds have been classified on the basis of number of carbon atoms in a ring. Small rings consist of 3 to 4 carbon atoms. Common or the normal rings are found to have 5 to 7 carbon atoms. Medium rings have 8 to 11 carbon atoms, whereas the large rings consist of more than 12 carbon atoms. Many chemical properties depend upon the class of the cycloalkane, and these differences in the behavior were explained by the Bayer's angle strain theory. Bayer observed different bond angles for the different cycloalkanes and also observed some difference in their properties and the stability. Bayer proposed that optimum overlap of atomic orbitals is achieved for the bond angle of 109 degree and 28 minutes for carbon atom in a tetrahedral geometry, like in the case of the methane molecule. In short, it is ideal bond angle for an alkane compound. Effective and optimum overlap of atomic orbitals produce maximum bond strength and a stable molecule. If bond angles deviate from an ideal value, then the ring produces a strain in a complete system. Higher the strain in the ring, higher would be this instability. Also, higher the strain produced, increased reactivity and increases the heat of combustion. On this basis, Bayer proposed a angle strain theory, which explains the reactivity and the stability of the cycloalkanes. Bayer proposed any deviation of a bond angle from an ideal bond angle value of 109 degree 28 minutes, which is most optimum for a tetrahedral carbon atom, produces a strain in a molecule. The Bayer's theory is based upon some assumptions which are helpful in understanding the instability of a cycloalkane ring systems. These assumptions are: all the ring systems are planar. Deviation from a normal tetrahedral angles lead to unstable cycloalkanes. The large ring systems involve negative strain, hence do not exist. The bond angles in cyclohexane and higher cycloalkanes, for example, cycloheptane, cyclooctane, cyclononane, etc., are not larger than 109 degree 28 minutes or 109.5 degrees, because the carbon rings of those compounds are not planar or flat, but they are puckered. In other words, they are wrinkled and they have deviated from their normal planar structures. The distortion of each ring size assuming cycloalkane rings to be planar. Cycloalkane. The ring of cyclopropane is triangle, all the three angles are of 60 degrees in place of 109.5 degrees, which is a normal bond angle for a carbon atom, to adjust them into a triangular ring system. Thus, deviation would be, which is a normal tetrahedral bond angle minus the actual bond angle, which is 109.5 degrees minus 60 degrees, which is equivalent to 49.5 degrees. In case of cyclobutane, the ring of cyclobutane is square and the bond angles are 90 degrees in its place of 109.5 degrees, which is required to adjust them into a square ring system. Thus, the deviation is equivalent to 109 degrees 5 minutes minus 90 degrees, which is equal to 19.5 degrees. Since deviation from the normal bond angle is higher for a cyclopropane, which is 49.5 degrees, than cyclobutane, which showed the deviation of 19.5 degrees, therefore, cyclopropane has higher strain, which makes it less stable in comparison to cyclobutane. As a result, cyclopropane is more prone to undergo ring opening reactions as compared to cyclobutane. According to Baer, the relative order of stability of some common cycloalkane would be cyclopentane more stable as compared to cyclohexane, which is in turn more stable than cyclobutane and cyclopropane. But the actual observed order of stability for these cycloalkanes, cyclohexane, cyclopentane, cyclobutane, and finally the cyclopropane. Synthesis of small ring compounds. Synthesis of cyclopropane ring. Few important methods for the synthesis of the cyclopropane ring can be summarized as from 1,3-dibromopropane. The cyclization of 1,3-dibromopropane using sodium metal under the anhydrous conditions gives cyclopropane. The reaction follows the pathway of Woods coupling reaction as shown in the given scheme. The yield of this reaction can be improved by using zinc metal. As can be seen, the two bromo groups are taken up by the sodium metal and released as sodium bromide, and the cyclization of a three-membered carbon ring is going to take place to form cyclopropane. Instead of sodium, if zinc is used, as we said, the yields are found to be better. From 1,2-dibromopropane. The 1,2-dibromopropane can be cyclized on reaction with malonic acid diethyl ester in presence of a base, sodium acetate, to give cyclopropane ring. The reaction is shown in a given scheme where 1,2-dibromopropane is treated with malonic acid diethyl ester in presence of sodium ethoxide, and the cyclization reaction takes place leading to the formation of an ester. The compound is further hydrolyzed with the decarboxylation taking place leading to the formation of a cyclopropane carboxylic acid, which can in turn further be decarboxylated to form cyclopropane. From 1-bromo-3-cyanopropane. 1-bromo-3-cyanopropane in the presence of a base like sodium hydroxide is cyclized to form cyclopropane carbonitrile, which on hydrolysis forms cyclopropane carboxylic acid from alkenes using Simmons-Smith reaction. In this reaction, iodomethyl zinc iodide is the reactive carbenoid intermediate formed by the reaction between diiodomethane and a zinc copper couple. Alkenes on reaction with iodomethyl zinc iodide form cyclopropane derivative via a concerted reaction. Here the nucleophilic carbon-carbon double bond causes the loss of the iodide ion. As the leaving group, and the electrons from the nucleophilic carbon-zinc bond are being used to form the other carbon-carbon single bond. Thus, both the new carbon-carbon single bonds are formed simultaneously as shown in the given scheme, and henceforth this reaction is also called as a concerted reaction. As can be seen in the given scheme, iodomethane plus zinc copper couple in the presence of ether is forming a complex which, when treated with the alkene compound, leads to the cyclization, concerted mechanism of addition and the formation and the bond breaking taking place, leading to the formation of a substituted cyclopropane. Major drawback of this reaction is the high cost of diiodomethane. Substituents that are trans in the alkene are trans in the cyclopropane, while the substituents that are cis in the alkenes are cis in the cyclopropane. Hence, the stereochemistry of the reaction is maintained and the reaction becomes a concerted reaction. The stereochemistry of the cyclopropane using the Simmons-Smith reaction is further has been shown in the next two examples, wherein the trans substituents remains trans while the cis substituents remain at the cis position. From diazo compounds. Diazo compounds like diazomethane reacts with alkenes and form cyclopropanes. The reaction takes place in two steps. The first step of 1,3-dipolar cycloaddition. The activated alkene like but-2-ene-dioic acid diethyl ester reacts with diazomethane at 1 and 3 position, forming the corresponding pyrazole derivative 4,5-dihydro-3H-pyrazole 3,4-dicarboxylic acid diethyl ester. Is the nitrogen removal. The pyrazole derivative 4,5-dihydro-3H-pyrazole 3,4-dicarboxylic acid diethyl ester on either photochemical or thermal decomposition loses one molecule of nitrogen and forms a cyclopropane. The reaction is taking place in the presence of copper on heating, or it is a photochemical reaction. If the above reaction is carried out using potassium hydroxide and platinum as a catalyst via a thermal route, it is known as Kirchner cyclopropane synthesis. Cyclopropane can be prepared from alkenes. Alkene on reaction with carbene like methylene forms cyclopropane via cyclic transition state to form cyclopropane ring. The reaction of but-1-ene with methylene gives ethyl cyclopropane. As shown in the scheme, the reaction of isobutene with methylene gives 1,1-dimethyl cyclopropane, whereas the reaction of cyclohexene with methylene gives bicycle 4,1,0 heptane as shown in the scheme. Synthesis of cyclobutane ring. Few important methods for the synthesis of the cyclobutane ring are shown from 1,3-dibromopropane. The reaction of 1,3-dibromopropane with malonic acid diethyl ester in presence of a base, sodium acetate, gives a cyclized product. Cyclobutane 1,1-dicarboxylic acid diethyl ester, which on hydrolysis gives cyclobutane 1,1-dicarboxylic acid as shown. Other methods used to convert cyclobutane carboxylic acid to cyclobutane are given as in the presence of the silver salts or bromine, wherein the bromine is substituted in the place of carboxylic acid, which undergoes the Grignard reaction in the presence of the acid to form the cyclobutane. Furthermore, the reduction to the alcoholic group could be carried out using lithium aluminium hydride, which can further be reduced in the presence of hydrogen and nickel to form cyclobutane. By non-reversible cyclization, the reaction of 5-bromo, 1-phenyl, pentane, 1-one with suitable base leads to the cyclization and formation of cyclobutane derivatives. As shown in the scheme 9, 5-bromo, 1-phenyl, pentane, 1-one undergoes the reaction in the presence of a base to form a carbanion, which undergoes intramolecular alkylation leading to the formation of a cyclobutyl derivative from difluoro-dichloroethene. Difluoro-dichloroethene on heating at 200 degrees centigrade dimerizes to form 1,1,2,2 tetrachloro 3,3,4,4 tetrafluorocyclobutane as shown in scheme. This is also called as 2+2 cycloaddition reaction. The reaction is carried out at high temperature of 200 degrees centigrade. The reactions of small ring compounds. The reactions of cyclopropane. Cyclopropane, having a boiling point of -33 degrees centigrade, is one of the best anesthetists known. The cyclopropane ring undergoes ring substitution and ring opening reactions. Some reactions like halogenation. Cyclopropane undergoes halogenations in the presence of sunlight via a free radical substitution reaction. For example, cyclopropane undergoes chlorination in the presence of sunlight to form chlorocyclopropane. Addition reactions. Due to the increased pi character in the carbon-carbon bonds of cyclopropane, it reacts like an alkene in the certain cases. For example, hydrohalogenation. Cyclopropane undergoes hydrohalogenation with mineral acids to form a linear alkyl halide. The cyclic ring opens up to lead to the substitution reaction. Substituted cyclopropanes follow the Markovnikov rule in their addition to HBr. The bromo group goes to the carbon atom bearing the lesser number of hydrogen atoms, whereas the hydrogen goes to the carbon atom bearing more number of the hydrogen atom, leading to the formation of 2-bromobutane. Bromination. Cyclopropane undergoes bromination in the presence of Lewis acid catalysts like FeBr3 and forms 1,3-dibromoalkane. Hydrogenation. Cyclopropane undergoes hydrogenation in the presence of ranitol at 80 degrees centigrade to form a propane. These are all ring opening reactions. Hydration. Cyclopropane undergoes water addition in the presence of concentrated sulfuric acid used as catalyst and forms propanol. The reaction takes place by the addition of hydrogen at one carbon atom and the addition of OH group on the other carbon atom, leading to the formation of the alcoholic system. But like alkenes, cyclopropane does hydroxylated and show oxidation reactions with ozone. With ozone, it does not undergo any reaction. Reactions of cyclobutane. Cyclobutane has a boiling point of -15 degrees centigrade and is resistant to thermolysis, but decomposed at 500 degrees centigrade to ethane. The cyclobutane ring undergoes ring substitution and ring opening reactions. Some of the reactions like the ring expansion to cyclobutane, halogenation with chlorine as the photochemical radiations forming a substituted chlorocyclobutane, the ring opening and the reduction taking place at 200 degrees centigrade in the presence of hydrogen and nickel to form butane, at 500 degrees centigrade to form a alkene system, and the hydrohalogenation taking place to form the open chain halogenated product. Cyclobutane reacts with hydrogen halides to give halobutane and with chlorine molecule in the presence of light to give chlorocyclobutane. The cyclobutane ring opens up on treatment with hydrogen over metal catalyst to give butane as the product. The cyclobutane also undergoes ring expansion reactions to give the higher cycloalkanes. To summarize what we have done till now, the alicyclic compounds are organic compounds that resemble both aliphatic and the cyclic compounds in their properties. Monocyclic compounds have been classified on the basis of the number of carbon atoms in the ring in the following way. Small rings 3 to 4 carbon atoms, common or the normal rings 5 to 7 carbon atoms, medium rings 8 to 11 carbon atoms, large rings more than 12 carbon atoms. Bayes angle strain theory. Bayer proposed that the optimum overlap for the atomic orbital is achieved for the bond angle of 109 degree 28 minutes for the carbon atom in tetrahedral geometry. Any deviation from the normal bond angle is higher for cyclopropane and than cyclobutane. Therefore, the cyclopropane has higher strain, which makes it less stable in comparison to cyclobutane. Synthesis of cyclopropane ring can be achieved from 1,3-dibromopropane, 1,2-dibromopropane, 1-bromo-3-cyanopropane, alkenes using Simmons-Smith reaction and diazo compounds, etc. Synthesis of cyclobutane ring can be achieved from 1,3-dibromopropane, non-reversible cyclization and 2+2 cycloaddition. The cyclopropane ring undergoes ring substitution and ring opening reactions. Cyclobutane reacts with hydrogen halides to give halobutane, with chlorine molecule to give chlorocyclobutane. Cyclobutane ring opens up on the treatment with hydrogen over metal catalyst to give butane as a product. It also undergoes ring expansion reactions to give the higher cycloalkanes.